What is a sequence? Don't look at your note sheet. What is a sequence? When you hear the word sequence, what do you think? Pattern. Okay, an ordered progression of numbers that follow a pattern. I think that is a great way to say it. A sequence is an ordered progression of numbers. That's why I didn't mean to hand out the notes, and then I did, and it was too late. Okay? The domain of a sequence is the set of positive integers. What's an integer? It's like the whole numbers with the negative. Okay, yeah. So an integer is a number that, like 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Okay, no fractions, no decimals, just an integer. Okay, so the domain is the set of positive integers. So we plug in 1, we plug in 2, we plug in 3, we plug in 4. Okay.
Isn't that called like natural numbers or something?
Yes, natural numbers. You are correct. Now, I will say there will be some sequences you will see that will start at 0 instead of 1. And we'll talk about those as they come across our plate. But for the most part, we're plugging in positive integers, sometimes 0. Okay? No negative numbers. Okay? So there's two different types of sequences. There's finite versus infinite. What is the difference? Okay, the infinite sequence goes on forever, but the finite sequence stops.
Doesn't like the infinite when you go by a certain infinite matter, like plugging in.
Okay, so you're thinking of what we're probably going to be doing tomorrow and Friday, okay? Today we're really talking in general what's happening with our sequences and series, and then tomorrow and Friday I'm going to give you some specific guidelines for specific types of sequences and series, okay? So today we're talking very much in general, okay? So an explicit, I feel like there was more to that sign, wasn't there?
There's a little blank there.
Yeah.
Instead of function notation. Aha, there it is. Okay. Instead of function notation, we're not working with functions, we're working with sequences. So we're not working with x even. You're going to be seeing n's for that natural numbers, okay? And instead of f of x, you're going to see a sub n. So if you see a sub 1, that means the first term. If you see a sub 25, that means the 25th term. Now raise your hand if you learned a little bit about sequences and series last year in your math class.
Raise your hand.
What? You don't like it?
Oh, it's not like a test you had to take like the first time.
In my class, no one understood, and I think like.
Well, you know what? Here is your opportunity to understand it. Okay?
I think in my class, like,
We're gonna
off because of this.
we're gonna learn from our mistakes from last year. Come on.
Okay. An explicit sequence looks like a formula. Okay? This is an explicit sequence because it's written as a formula. Okay? All we have to do is plug in our positive integers. Okay? So if we want our first term, then we are going to plug in 1 for n. What is our first term?
The following groups need to go to the gym: Culinary Club, ProStars, Debate, and Leo Club. Again, that's Culinary Club, ProStars, Debate, and Leo Club. I
I think it'll be more closer to second hour. Okay. For our second term, we're gonna plug in 2. 2 squared plus 1 is 5. Our third term, a sub 3, we plug 3 in for n. So we get 10. Our fourth term, we plug 4 in for n to get 17. Our sequence is 2, 5, 10, 17. I bet we could even figure out the fifth term without writing it down. What would it be? 26. And that would keep on going. Here's another one. Example 2. Oh, you don't have to write it down. Isn't this nice? You don't have to write it down. Okay. Ms. Sparky and I are trying to save some time with this since all the notation is a little bit funky, instead of you having to write it down. Okay. Our first term means we're plugging in 1 for n. What would our numerator be if we plug in 1? Say negative 3. And our denominator would be 3. So our first term is negative 1. Our second term, if we plug 2 in for n, 3 times negative 1 squared would be what? It would be a positive 3, and our denominator would be 5. Our third term, 3 times negative 1 cubed over 7. Our fourth term, 3 times negative 1 to the fourth, 3 over 2 times 4 plus 1, 9, so we have 1/3. And a sub 5, 3 times negative 1 to the fifth, negative 3 over 11. So our sequence is negative 1, 3/5, negative 3/7, 1/3, negative 3/11, and it would keep on going. Okay. If it said find the first 5 terms of the sequence, you would not put that ... because it would be finite. But if it doesn't give you any instruction, then we're going to assume that it's infinite. Okay? Now I'm going to give you an opportunity to find me the sequence for example 3. Please work together at your pod.
Hey, Nick, what's up, man? Did you get your picture taken? You smile real nice?
Friday.
I'll be glad.
Because we can only calculate right
All right.
now our knowledge.
Well,
Our common ratios of it.
I believe that this is approximately.
Okay.
I think these are just going to flip the negatives.
Thanks, Donna.
I believe, yes. I don't really feel like doing more assessment.
Oh, yeah, yeah.
Because it's n plus 1 instead of just n. So every odd integer is going to be an even
It just
answer,
flips the
and
negatives.
every even integer or negative. Just like the sign. Basically.
Okay. What happens? If the same sequence except the signs are flipped. Okay? Do you notice that? Okay? What I want you to see here is that whether we have -1 to the n plus 1 or -1 to the n, we're going to get that sign variation of negative, positive, negative, positive, negative, positive, right? Well, if we want to start with a positive for our first term, we need -1 to the n plus 1. But if we're going to start with our first term being negative, we want to see -1 to the n. Okay, so if you see a sequence that is alternating in sign, you know that it's going to need to be multiplied by -1 to either n or n plus 1. Okay, so we're going to practice writing some sequences here. Okay, now we're going to have to think outside of the box, but I will tell you tomorrow I'm going to teach you about a specific kind of sequence, and Friday I'm going to teach you about a specific kind of sequence. So don't panic too much. 1, 5, 9, 13, 17. What kind of pattern do you see happening here?
Approximately it goes up by 4.
It is going up by 4. Okay, so we need to figure out a way to write an equation to where when I plug in 1, I get 1. And when I plug in 2, I get 5. And when I plug in 3, I get 9. Because what's happening is this is our first term, this is our second term, this is our third term, fourth term, fifth term. So we need to write an equation to where when we plug those numbers in, we can get that. Okay, so we have a change of 4. It is a constant change. What do we know that change is constant? What is a word in math that has a constant change? Slope, it describes a constant change, right? Okay, so since our constant change is 4, I'm going to say 4 times n. But if I plug in 1, I get 4. So what should we add or subtract onto this? Minus 3. When I plug in 1, we get 1. If we plug in 2, 8 minus 3 is 5. If we plug in 3, 12 minus 3 is 9. We get those terms. Okay. Okay. Example 5. 2, -9, 28, -65, 126. Do you notice how the signs are changing? Okay. So we know we need a -1 to a power. Do we need the n or the n plus 1 power? Say it louder. N plus 1. Because we want that first term to be positive, second term to be negative. Now, we need to think outside the box. These numbers, 2, 9, 28, 65, they're not special numbers, but they are very close to a set of special numbers. There may be one away from a set of special numbers. Special numbers, think of like perfect squares. Oh, they're very close to perfect cubes. How far away are they from perfect cubes? Okay, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64. Okay, so to get 2, 9, 28, 65, we're taking that perfect cube and we're adding 1 to it. Now, we're going to get into tomorrow and Friday specific rules to write these equations, but for tonight's homework, you're gonna need to think outside the box, and you're gonna need to be able to just do some trial and error. If you don't get it the first time, try again. If you don't get it the second time, try again. But do not give up easily. Okay, that's not an option. Okay? There are actually two different ways to write sequences, and I will expect you to be able to do that. The second way is a recursive sequence. So we just worked with a bunch of explicit sequences. Now I want to work with some recursive recursive sequences. Okay?
The following groups need to go to the gym: DECA, Drama, and International Thespian Society. Again, DECA, Drama, and International Thespian Society.
Fun.
Okay, so in a recursive definition, you are going to define the first term, and then you're going to describe how the next terms are related. Okay, and you see an example here. This is the first term. Okay. Here is a term. And basically, it's describing how the previous term is related. So, I'm going to change this. Sorry, next or previous, because you could do it either way. Okay? So, in this definition, I'm describing how the previous term is related. So, the term that I'm trying to find, a sub n, is a sub n minus 1. So, that means the term before plus 1, or plus 5. When you see that subscript a sub n minus 1, that just means the term before.
We also need the Forensics Club to go to the gym. Again, the Forensics Club.
Okay. So we're going to do some examples, which are on the next page. So I'll let you flip. Okay, so our first term is 3. If we're finding our second term, okay, so essentially n is 2. Do you agree? Okay, so if a sub n is negative a sub n minus 1 plus 5, we have negative, since I'm talking about a sub 2, this would mean a sub 1. So basically we have negative a sub 1 plus 5. Well, what is a sub 1? Okay, so what we have is negative 3 plus 5, which is 2. Okay. When we talk about the third term, since a sub n is negative a sub n minus 1 plus 5, essentially n is 3, right? So if we talk about negative a sub n minus 1, that would be a sub 2. Okay, well we know that our second term is 2. So what we have is negative 2 plus 5, which is 3. Is it? Callie thinks that maybe we're going to see some back and forth action here, right? When we find the fourth term, if we look at our recursive definition, we have negative a sub n minus 1. If we're looking at the fourth term, then that would be the third term, negative third term plus 5, which is 2. Okay, and we see a pattern here. right? Our sequence is 3, 2, 3, 2, and that is going to keep going. Sometimes the projector's like bumped there. Okay, now sometimes you will see two terms defined, and then your recursive definition is written in terms of the previous two terms. Yes? Yeah. So I must have had a copy paste issue. Please, I want a sub 1 to be 4 and a sub 2 to be -2, so please fix your notes. What?
I just wondered how you're gonna do it if you didn't have.
Right.
Sub 2.
Correct. So since our recursive definition is written in terms of the previous two, we gotta have two terms to start with, which is nice because it's less work for you, right? A sub 1 is 4. A sub 2 is -2. So if I'm looking at a sub 3, a sub n minus 1, that means the term before, so the second term, times a sub n minus 2, well, that means the term 2 before, which in this case is term 1. So what we have is 4 times -2, which is -8. Okay. Our fourth term would be the term previous times the term 2 previous. So the third times the second term. So -8 times -2 is -16. What? Oh, I'm sorry, that is positive. I wrote -8, but I was not thinking about that negative. And then our fifth term would be term previous, fourth term, times 2 previous, third term. So 16 times -8, which would be, what? -128. So our sequence would be 4, -2, -8, 16, -128. Okay. A lot of this is getting used to the notation and whatnot. Okay. Questions so far? All right. Let's talk about some factorials. Oh, I think this is in a little backwards order. What is this sequence? The Fibonacci sequence. Technically, we could write this as a recursive, right? First term is 1, second term is 2, and then we add the previous two terms to get to the next one. Okay? The Fibonacci sequence. Did you guys do a project with the Fibonacci sequence last year? Or no? 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 Okay. I know that was a thing before. But, okay. I wish we had more time to talk about it today, but we're a little scrunched for time. Factorial. Do you remember factorials? Okay. Good. And so 5 factorial means 1 times 2 times 3 times 4 times 5. Right? 6 factorial. I like to think of it as 6 times 5 times 4 times 3 times 4. Okay? All the way until 1. So if we want to reduce 8 factorial divided by 2 factorial, 6 factorial, we know that 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So what happens? Those cancel. Right, right. So we're taking 8 times 7, which is divided by 2, 28. Okay, what you're saying, Caleb, is we know that this is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So instead of writing it out, you could write that as 6 factorial. So then you wouldn't have to write it out again here, and you could just cancel those. Okay, that would be less writing if you wanted it that way. Also, that's going to help us with this next example. Okay, if we want to reduce n plus 1 factorial over n factorial, well, what does n plus 1 factorial mean? Okay, right. So if we're talking about 8 factorial in the denominator, then we have 9 factorial upstairs, right? So this is what we can do. We know n plus 1 factorial would have to be n plus 1 times n minus 1 times n minus 2 times n minus 3 all the way until 1, right? So n plus 1 times n factorial is how we could write that. See what I mean there? Okay. So if we're dividing by n factorial, we are left with n plus 1. Yes?
I don't really get how you have a numerator.
Okay, so factorial just means you start at that number and then you multiply by the next lowest integer and then you multiply by the next lowest integer all the way until 1, right? So we start by taking n plus 1 and then we multiply by n and then we multiply by n minus 1 all the way down until 1, right? So kind of like we did up here. Instead of like writing it all out, we wrote 8 factorial as 8 times 7 times 6 factorial. That's what I did with that n plus 1. Does that make sense?
Yeah.
Okay, just, and you can write it all out if you want to, okay? You can write that this is n plus 1 times n minus 1 times n minus 2 all the way until 3 times 2 times 1. And you can write n factorial as n times n minus 1 times n minus 2 times all the way until 3 times 2 times 1. And then you could cancel out that way if that's a better visual for you. Okay. Okay, it is very important that you understand the difference between a sequence and a series. A sequence was a what? An ordered progression of numbers, right? Okay. Now, a series is the sum of a sequence. Okay, so you've seen this symbol before, right? Okay. This right here tells you where to start. This right here tells you where to stop. Okay. And so you plug in numbers until you have what you need. So, if we're talking about this sum right here, we're going to plug in 1 for the letter I, and then we're gonna plug in 2, and then we're gonna plug in 3, and we're gonna stop when we plug in 5, okay? So this is going to be 3 times 1, plus 3 times 2, plus 3 times 3, plus 3 times 4, plus 3 times 5. We hit 5, so we're going to stop. What do we have here? 45? Sounds good to me. Okay. Now the next example I have for you looks a little bit different. Okay, where do we start plugging in numbers here? At 3, so we start by plugging in 3, then we plug in 4, then we plug in 5, then we're going to stop once we plug in 6 because that's the number that we have right here.
Hey, Nick. So good.
Okay, so what do we get here? $90. Okay. All right, we're almost there, guys. Wednesday's really cutting out our minutes. Okay. We're not going to worry about these right now. Okay, so I do want to tell you that we could have an infinite series. And this is going to be very important on Friday when we talk about the specific geometric sequence, okay? But it is okay to have an infinity up here. It just means it's literally going to keep going to infinity, okay? How the heck is that possible? Okay, so an nth partial sum means we stop at whatever n is. An infinite series means we go to infinity. So you see you have 2 examples, right? And they look the same. If I ask for the third partial sum, how many terms are you adding up? 3. You're adding up the first term plus the second term plus the third term. So 3 tenths, 3 100ths, 3 1,000ths would add up to be 0.333. Wait for it, wait for it. What if I ask you for the infinite series? We would have 3 tenths plus 3 100ths plus 3 1,000ths plus 3 10,000ths. And that's going to keep going on forever. What do we got here, people? We have 1/3. 0.333333333. 0.3 repeating is 1/3. Okay, please listen carefully. You need to attempt every problem, and you need to problem solve through the ones that you struggle with. Tomorrow I am gone with kids to a math competition. The sub will give you time to talk about your homework with each other. If somebody got a problem that somebody else can't figure it out, come up to the board, show people how to do it. And then you're going to watch a video about 9.2, so make sure you bring these yellow packets so that you can take notes on 9.2. Those of you who are in and out, get the notes by either watching this video, hello for the second time, or looking at it from a neighbor. Okay? I'm just saying if you watch this again, you know, can you say hello?
Oh, got it.
Now, I'm not wrong. We get out at 9:07, right?
Beats me. Yes.
I was like, oh, I really hope I didn't like.
Stop checking.
That has happened to me before.
I think the worksheet today.